Hello. Hi again. Are you going in?
Yeah.
Oh, are you? How's it going?
Hello.
How are you? Good. I'm back. You're going to be a YouTube star. It's going to be great. So you're going to be a YouTube star.
But I've always dreamed of.
I made it. So go ahead, sit in your chair.
Yeah, go ahead. I won't be going back there. The papers in the binder are not organized, but they are there.
Okay. I'll organize them.
Oh, thanks.
There's a whole punchy setting that I will show you. It'll make your life easier on the printer.
Hold on just 1 second. Can you wait for me outside?
Do you line them up to come in?
I do not, but I'm also on the way now, but not telling me to come out. Oh, no. It's not connecting. Yeah. All right, sorry about the wait. You can start coming in. Grab both of those papers and find your seats. Grab both of the papers and your seats.
Miss, just saying, there's a lot, there's people that go that one.
As long as you're back, you can put it there. Oh, thanks. All right, good morning, everyone. First, I want everybody's voices off and eyes on the board. I'm going to play this video, but it's going to be real quick, so make sure you're paying attention. Okay.
This science stuff is very serious. One ball is wooden and the other is brass. This time we have 3 balls. We're adding a ping pong ball. You can see here.
Okay, so I know that was pretty quick. You guys might have some questions. The first one is why are they floating? And the reason for that is that this experiment was done in space. So this experiment was done on the International Space Station with no gravity. So there's no gravity pulling it down, which is why it's just floating up there. So when I say go, with your tables, I want you to take 2 minutes and think why some of the balls went further than the other ones. Why, when the man blew air at them and propelled them forward, the ping pong ball flew super far, but the one made of brass stay right here. All right, take 2 minutes to do that. Get started. No, yeah.
Balls are different to the golf ball, it's heavier than the actual. There's no ball to it. I'm on it.
Yes, Morgan.
I haven't been doing my job well, but you're taking it.
Yes, I do.
Yes.
Jay? Here. Natalie?
No.
Noel? Here. Morgan?
Here.
Juan? Marco? Leoncio?
The
Riley?
volume of the objects are different.
Right?
Here.
Catherine? Catherine? Jose? Armando? Okay.
Oh, no.
Where am I? Armando? Okay. Stefania? Here. Catherine? Here. Anthony? Brian? Michael? Inel? Brian Ortega? Nancy? Here. Aileen? Here. Brian? Melanie? Here. Dalian? Okay. Leslie? Here. Jocelyn? Kenya? Here. Dana? Here. Joseph? And William?
Here.
Okay. Math.
Yes.
Math.
Yes.
All right. Who's got an answer for me? Who thinks they know why? Morgan.
Our table said because the volume is different and you have to take into consideration the object's weight.
Okay. So if the balls are the same size, would the volume be different? If they're occupying the same space.
Like the mass is maybe
The
what I
mass?
was trying to say. Maybe.
Okay. Elaborate on that.
Like if the balls are different weights, then it's easier to blow one than the other because it moves easier.
Okay. So you're saying they're different weights? So for right now, I'm going to ask you to keep using the word mass that you said first because mass and weight are different things. We're going to go into it in a few days and I'll explain the difference. But for right now, keep using the word mass. Okay. Can somebody tell me why the masses are different?
Because one is like made of, they said steel, right?
Brass.
Brass, the other one is wooden, and the other one is just plastic. And so all those three different elements, they're heavier than each other. Like one is lighter, the other one is heavier, or still lighter. So like if it's lighter, it goes faster, or like it goes away.
Okay, so you think because they're made of different materials, some of them are heavier, some of them are lighter, and then the lighter ones go farther? Yeah? What about what's inside the ping pong ball? Air? What's inside the wooden ball? Wood. So one of them is hollow and the other one isn't. That also depends how much mass things have. Because the ping pong ball just has air inside it, but the wooden and the brass balls, they're solid all the way through. So that makes a difference in how much mass things have. Okay, you should all be on your Explorers, so the document that you picked up that has a picture of the chicken on the front. So make sure you find the chickens. Everybody should have the chicken. Okay. So what I want you to do is to work with your table groups, and we're going to go through what we're doing today. So the first thing that we're doing is that we're looking at this table about this chicken. Right now, I've grayed out the mass column, so we're not focusing on mass. We're just looking at force and acceleration. So just the force on the chicken, how hard I'm pushing it, and the acceleration, which is how much it's speeding up. Everybody good?
Yes,
For
ma'am.
the chicken? Okay, so, take 4 minutes. What we're going to do is we're going to look at any trends or any patterns that we see in this table. I'm going to put it up on the board so that we can have a look at it. So look at any trends or any patterns that you see, discuss it with your tables, and then try and write that down in words. What patterns do you see in this table? Take 4 minutes to do that, get started.
So each one is 1.3. Yeah.
So change the word.
Just round up to 4. Yeah, 36 line and round up to 4, so each value of the chicken is increasing by the donation of 1.6. Oh, I'm sorry, this one. Am I correct? Can you do my math on it? Can you do my math on it? Am I correct? Each one is 1.6 acceleration and 1.349. Yeah. So start with 3.
Well, I think it's 0 to be a 0, right? I think it's showing that it has right there.
Oh.
Figure out what happened.
Then it can't.
Well, let's check, right? What is the acceleration? What are the 3 things? Velocity is constant, the acceleration is 0, and the net force is 0 as well. Now, the acceleration is 0. What's that?
Yeah, now you see where I'm coming from.
It's not going, okay.
So it goes from 3 to 6 to 2. Yeah.
Okay, so if we got 3 to 6 times what?
Times 2.
Around this side.
1.3. That's what 1 is. 2 is that divide, and it's like 1.341. What are these? Divide 2, right? Divide 2. When I was doing this, I divided that 2, divided that 2.
Net force, okay. What else do we miss?
And she's trying to say that
Okay,
it's
so
changing.
we're saying, is it doubling? What is happening?
Okay.
Everyone.
Yeah, every,
Okay, yeah, that's true. You're right.
How much?
What do you think this one is? I want to hear you them here. What do you think
So,
for the number?
4, so 2 times 2 is 4, 4 times 2 is 4.
The one above it.
That force doubles with the
Yeah, for the 12 years.
Why would that make sense?
What is it, like, figured out that there's a ratio?
Okay, how'd you get that?
I don't because I feel like it's here.
All right, let's wrap up those discussions. Have eyes back up here and voices on in 3 and 2 and 1. Okay, over here. So, real quick, this table, one thing that you saw, one pattern.
My support increases, the acceleration also.
Okay, so you're saying that as force is going from here down, it's increasing, and the same thing is happening to the acceleration, it's also increasing? Okay, something else. One other pattern. What do we see? Yes?
We did the math behind it, and we said it's accelerating each time, like every one by 1.341.
Okay, so you tried to find a ratio between those things? So you found like a ratio when force is 3, acceleration is 4?
Yes.
So you're going to say that that's the ratio that you found between those two things?
Not necessarily.
Not exactly?
So we're trying to say like every one it's increasing. So I did 2n divided by 2.67 and trying to see like how is it increasing every time. And I think that each one is 1.341, but it gets more complicated because it doesn't just go 3, 4, 5. It starts speeding up like 6, 12. So we're trying to narrow down. So like if we were in the instance to find the acceleration of 12n, we could.
Okay. All right, somebody tell me what's happening to the force from 3 to 6. I saw some people up here. What's happening? It's doubling? What's happening to the acceleration from 4 to 8? Okay, so that's doubling right there. What's happening to the force from 3 to 12? Quadruple, so it's getting multiplied by 4? Yeah? What's happening here? We don't know.
It must be
What do you think would happen? You think it would also be multiplied by 4?
Yes.
Okay, so if I do that, I put a times 4 here. So 4 times 4, give me 16. Does that look right? Did anybody get that number on their papers? A few people? Okay, so a few people have gotten that number right there. Yes, yeah.
Another one is 16 to 30 here,
Yeah,
times 5, and then also an acceleration, 8 to 40, we also multiply that by 5.
so 8 to 40, this one right here, this is multiplied by 5. Okay, so we're seeing a pattern emerge. Every time force is multiplied by something, acceleration is multiplied by the same thing. So what do we get to the last question? Does anybody think they know what directly proportional means? Force and acceleration have a directly proportional relationship. Who thinks they know what that means? Marco.
Doesn't matter, each time that something affects one side, like something affects that force, it's also going to affect the acceleration.
Okay. Yes, Brian.
What I said that, proportion means that, if one side is being, affected by a number, the other side will be affected by that same number.
That's right. Both of those are correct. So what directly proportional means, that they increase the same way. That doesn't mean we're just adding, so from 3 to 6, we're not just adding 3 here, but we're multiplying. They're increasing by the same factor. So this is saying that if I push twice as hard on this chicken, it's going to go flying twice as fast. Okay? All right, flip to the back page of your score document. I'm going to come back. All right, so now on the back page of your score documents, there's a table here. This is showing you the acceleration of the chicken when I push it different ways. So this is showing you the force, and then, wait, what's happening here? Sorry. All right. My bad. We're on the back page. It should have a picture of a rock. That was my mistake. I went back up and then confused myself. All right. So you should have the rock, and instead of having force, you now have mass. So you have these mass values and then the acceleration for those mass values. So these are different rocks, and these are the accelerations of those rocks. So what I want you to do with your tables is to take 4 minutes and start graphing those. So you've got a little graph that I made for you. I know there's a hole punched through a part of it, but you should be able to graph that out. So start graphing those, and then tell me what pattern you see. Tell me what pattern you see here. Get started on that with your tables.
No, it's gonna be it is, yeah.
Are we ready for that?